Hello everyone. I am here to discuss our work, which has been accepted in the 18th International Conference on Automatic Face and Gesture Recognition, Istanbul, Turkey. So, title of our work is Neuro-Emotional Mapping of Human Emotions via EEG Signals, and the authors are Deepak Kumar, Pradeep Singh, Asutosh Kumar, Sutirtha Ghosh, and Balasubramanian Raman. So, this is the introduction of the presenter. My name is Deepak Kumar. I am a research scholar in the Department of Computer Science and Engineering at Indian Institute of Technology, Roorkee, under the supervision of Professor Balasubramanian Raman. So this is the outline of our work, I am going to present here. So introduction, background, methodology, results, conclusion, and then finally references. So what is emotion recognition? So emotion recognition is the process of identifying and interpreting human emotions using various techniques and technologies. It involves analyzing cues such as facial expressions, voice, and speech patterns, physiological signals like heart rate or EEG signals, and textual data to determine the emotional states of the individuals. So here are the key points about emotion recognitions. First one is techniques and modalities. There are many techniques and modalities that can be used to emotion recognition. First one is physiological signals. So physiological signals using data from sensor that measures heart rate, skin conductance, EEG brain activity, and other physiological responses. So next one is facial expressions. These facial expressions analyzing facial movements and expressions using computer vision algorithms to identify emotions. Voice and speech also another modality that can be used in the emotion recognition. Text analysis also one modality that analyze written text to detect emotions through natural language processing techniques. And there are many applications such as human computer interaction, healthcare, marketing and customer services, and like sports. So in healthcare monitoring, health and emotional well-being provides support in therapy settings and detecting early signs of emotional distress. Marketing and customer services understanding customer emotions to improve service uh, and enhance customer satisfaction. In sports also, we can use this emotion recognition like to know the emotional state of the particular athlete or uh, group of athletes. And there are many challenges in the human emotion recognition, such as accuracy and reliability. So, how to ensure that emotion recognition system accurately identifies emotions across different individuals and contexts. So, privacy and ethics also another concern. And so, addressing this concern related to the collecting, storage, and use of sensitive emotional data. Cultural difference is also another challenge that can account for variations in emotional expressions across different culture and ensuring the system is culturally sensitive or not. So multimodal data integration is another challenge. So if data is coming from different modalities, so combining data from multiple sources, let's say facial expressions, voice or physiological signals to improve the accuracy of emotion recognition systems. Data quality is another concern. So how to ensure that the data is uh, uh, accurate or not. So, and interpretation of the results is another challenge that can be that has in the emotion recognition domain. So there are many technological advancements in the field of emotion recognition, like machine learning and AI. So leveraging advanced algorithm to improve the accuracy and efficiency of emotion recognition systems. Another is multimodal approaches. So integrating data from various modalities to capture a more comprehensive picture of an individual's emotional state. So what is EEG signal? So EEG signal is a stand for electroencephalography, a non-invasive technique used to record electrical activities in the brain. So, what is the meaning of non-invasive technique? It it means that it does not require surgery or insertion of the instrument into the body, or which make it relatively safe and easy to use. So it measures the voltage fluctuations resulting from ionic current flow within the neurons of a brain. So EEG can provide insights into the various brain states and cognitive processes such as emotion, attention, arousal, meditation, and sleep states. Different patterns of EEG activity are associated with different mental states and behaviors. So the objective of this work is, let's say X denote the input containing the physiological signals, where X belong to R, N cross T cross C, where N is the number of samples, T is the time step, and the C is the number of channels that has been used in the EEG signal. So the objective is to classify a given electroencephalogram signal X of I into one of the six emotion classes, that is fear, joy, anger, sadness, disgust, and surprise. So in this work, we have used this data set where a total number of participants are 40, male participants are 24, female participants 16, and the age of the participant 70 to 57 years. Total samples are 70-22, which has been divided into three parts, which is training samples, validation samples, and test samples. And the recording duration for each sample is 15 seconds, and the subject repetition is 3 times, and the number of channels are 24 that has been used in this data set. So we have utilized three types of features in our work, and we have used three type of features in our work. First is time domain features, frequency domain features, and finally we have used entropy based features. So time domain features encapsulate the signals statical properties within the temporal dimension, while frequency domain features unite the spectral composition of EEG signals, offering insights into the power distribution across various frequency bands. And entropy based features encapsulate the signal's energy distribution across different frequency bands. So total we have used 22 features, in which there are time domain features, frequency domain features, and uh, uh, entropy based features. So as we can see here, we have used mean value of EEG signal, means that the average value of EEG signal over a specified period. Median value of the signal provides a measure of the central tendency that is less affected by outliers, and the variance of the signal measures the spread or dispersion of the signal's value, indicating the signal's variability. A standard deviation is the square root of the variance, representing the signal's dispersion around the mean, and the skewness describes the asymmetry of the signal's distribution, and the kurtosis of the EEG signal is the measure that tiltedness the signal's distribution, indicating the presence of outliers, and the zero crossing rate is the rate at which the signal changes signs, providing information about the signal's frequency content. And the number of waves is the total number of the count of waves in the signal, offering insights into the signal's rhythmic activity. The wave duration implies the length of the time a wave persists, then indicating the stability of the signal. And peak amplitude is the maximum value of the signal, which can highlight significant events or artifacts. And finally, the energy of the EEG signal is the total power of the signal, representing the overall activity level. And the next second type of features that we have used is frequency domain features. And the frequency domain features describe the signal's spectral properties by analyzing its frequency components. And these features provide insights into the power distribution across various frequency bands. And the key frequency domain features that we have used are delta power. This associates with deep sleep and consciousness states. Theta power, that we have used alpha power, beta power, gamma power, and sigma power of a EEG signal. And the sigma power associated with sleep and the certain stages of the sleep. And the total power that Welch power is an estimate of the power spectral density using Welch's method, which averages modified parallelograms to reduce noise. And finally, we have used in the third type of feature that we have used is entropy based feature. Entropy based features like quantify the complexity or unpredictability of the signal. And these features are derived from the signal's energy distribution across different frequency bands. And it provides a measure of signal regularity and complexity. And we in this type of we have used wavelet entropy of each signal. And wavelet and entropy evaluates the energy distribution across wavelet coefficients and capturing the signal's complexity and information content. And this higher entropy value indicate more complex and less predictive signals, while lower value suggests more regular and predictable patterns. So total we have used 22 features in our work. So this is the methodology that we have used. So total feature 22 features. This is the equation one represents the total feature that we have used in our work F1 to F22, and for each channel C, where FIC encapsulates a distinct characteristic of the EEG signal. And the final that the model that we have used is a random forest model in our work, and it is a collection of decision trees, let's say T1, T2 up to Tm, where each tree Ti is trained on bootstrap sample of training data, and the final prediction is obtained by aggregating the predictions of all trees through majority voting. And random forest has emerged as a robust classifier, and it also known as for its effectiveness in handling high dimensional data. Also, it is resilience against overfitting, and the ensemble nature of random forest classifier contributes to its high accuracy in complex classification tasks. So this is the overall architecture diagram of our work. As we can see here, we have EEG signal, and let's say user 1 to user n, and total number of channels that has been used in this work are 24. So channel 1 to channel 24, and we have extracted the three type of features, that is time domain feature, frequency domain feature, and entropy based feature for each channel. And after final extracting the features, that this data has been passed into the statistical descriptor has been passed into the grid search cross validation, and that after finalizing the hyperparameters, that tenfold cross validation is also used, and finally ML classifier used, and then that ML classifier is giving us the final label of the particular EEG signal. So this 10 cross tenfold cross validation is used to find out the best data. Let's say we have used 10%, 90% data at a time to train the model, and 10% data was left out. So after finalizing, we have used that the model which was giving the best performance with the 90% data that has been used in the training part, and the 10% has been left out. So it means that there was some data which was corrupted, and so that was that tenfold cross validation was able to find out that particular corrupted data. So these are the hyperparameters that has been used, and these parameters has been finalized using the grid search cross validation, as we can see in this table. So these are the results that we have find out. Like this is first row is the baseline that has been given with the challenge organizers, and we have also trained so many machine learning classifier like gradient boosting, support vector classifier, k nearest neighbor, and stacking classifier, decision tree, light gradient boosting, voting classifier, ADA boost, extreme gradient boosting, voting classifier, hard as well. And the random forest classifier was giving us the best validation accuracy, that was 0.2556. Even though voting classifier also giving the competitive results like 0.2389. But finally, we have used the random forest classifier for testing uh, the results. So this is the result table. As we can see here, this baseline that has been given, that was 0.1944, and our for validation set, and our was 0.2556 for validation set, while baseline for test set was 0. 1889 and ours was 0.2278. This is the confusion matrix for the validation set. And this is the leaderboard results that challenge leaderboard rank, and we were in the second position in this particular challenge, and our test accuracy was 0.2278, while the first position test accuracy was 0.2444. In terms of computation time, our was best. Like we in our model, it was taking 58.85 seconds, while the first position model was taking 111.5 minutes. So as we can say, in the computation time, we were like in the first position. So in the conclusion, so we have presented a detailed study on classifying human emotions using EEG signals, and our approach employs handcrafted features. Even though we have tried deep learning models as well, but because of a limited data set and the size of the data set was very small, so it was not giving the good results, and the model was overfitting. So that's why we have chosen the machine learning models in this work. And finally, in the future, we should try to expand this such kind of data sets and with more number of samples, so that we can like use deep learning models as well in the emotional classification using physiological signals. And it can be enhancing the model's generalizability and robustness as well. So these are the key references that we have used in our work. Thank you so much for listening.